Right, hello everyone. If you remember in the last video I was talking about calculus, differentiation, integration and all the rest of it. I just thought it's a good idea to talk about why differentiation works. And so for example, say if I have y equals 3x squared and I want to differentiate that, we said we get this power, so dy by dx then would be 2 times by 3, and then we remove or we decrease the power by 1, so we just get 6x to the power of 1. But then that might lead you to sort of the question, why do we multiply it, and also why do we decrease the power by 1? Why not 1.2? Why not pi? Why not a different number? So we're just going to sort of use it as a motivation to think about why it is just going to be 1. We're also just going to multiply the power by the coefficient. All right, so the idea comes from, obviously, gradients. We mentioned this is the gradient function. So if I have some random graph that looks a bit like, say, this here. Say I want say this is my f of x. Or you can call it y if you want. This is my x. I want the gradient, say, at this point here. Now we know that if I want a gradient, then I look for the gradient of the tangent at that point. So I would draw a tangent line at this point, so something that looks like this, and I basically want the gradient of that tangent line. So this line here would be sort of the gradient. Now if I choose a random point on this line here, this f of x, I could get a decent approximation to the gradient if I just chose this point here and drew a line from there to there. And if I somehow use these two coordinates, I could get a decent-ish approximation. So not the best, but of course I'm going to work towards improving that approximation. So I would, first let's just call this point here x. And if, say, the x coordinate of that point is x, then the y coordinate at that point could be y, or it would just be literally f of x. So this would be f of x, or the height at the point x. Similarly, if I choose this point here, well, I mean, I don't want to get too many variables involved, so I'll just say that this distance here, we'll call that a distance of h. So this point here, this x coordinate is going to be x plus some small amount h in this direction. It is a little bit possibly taking that to a bit of an extreme by making that quite big, but just bear with me for now. If this was f of x, then this point here, that's going to have a height of, and of course, if this is now the new x coordinate, don't get hung up with the x plus h is still just another x coordinate. It might have been 5. This would just be f of 5. So this would have a height of f of x plus h. And so the gradient of this line, we call this the secant line. This would be the tangent line, the true gradient, tangent. This would be my secant line. Secant line is similar to a chord in a circle. So if you remember circles, you've got a line like this, just touches the circle at 2 points. That's a chord. For a curve, a secant line is just a line that touches the curve at 2 points. So we've got a decent approximation for the gradient by using this gradient of the secant line. And so far, if I think about what an approximation would be for the gradient, I could say that m, the gradient, is going to be the difference in the y divided by the difference in the x. So it'd be y1 minus y2 over x1 minus x2. Well, let's just use these coordinates here and see what y1 and y2 would translate to. So I'm going to choose this one as the big one. So y1 can be this one. So the y coordinate is f of x plus h. y2 is the second y coordinate. So take away f of x. And of course, the distance, so if this is the first coordinate we chose, this was the second coordinate, then this would be the x1 and this would be the x2. And the difference between the x is, well, I could do x plus h, take away x, or I could just notice that the distance between these two is obviously just going to be h. And of course that's further enforced by the cancellation there. And so really what I've got here is an approximation for the gradient here. It's not the best, but we're going to use this now to try and improve our approximation. So we've got this thing here. Right. The next thing I want to do is try and see what would happen if I chose a better point for my approximation. So say I chose this point here. If I chose that point there and I drew another secant line, it would be a little bit better in that it's not going to be the best line. But you can see that it's a little bit shallower and it's actually closer to the true tangent line. So what I'm basically saying is, if I make this distance h here smaller and smaller, I'm getting a better and better approximation to my tangent line. So how am I gonna make that happen to this thing here? Well, I've got that this is a good approximation to the actual gradient, the true tangent. But I need to try and use some sort of maths to get a better approximation to it. So what I'm going to do then is I'm going to say I want that h to get really, really small. So what I'm going to say is, if I use the limit as h tends towards 0, so if I get this h and I make it really, really small, so that this sort of point here, this point that I'm using to approximate the gradient, if I make this sort of come closer and closer to the starting point, the bit that I actually want the gradient at, the point that I actually want to find the gradient at, what I'm actually doing is I'm taking the limit as h gets really, really small. So I'm taking the limit of this little expression here, and that expression is obviously f of x plus h minus f of x divided by just h. And of course we've got a little bit of a problem here because we're going to be dividing by something that's getting smaller and smaller, so that we might expect that to just blow up to infinity. But you'll notice that if you work it properly and you do a good manipulation with the algebra, or proper manipulation rather, you'll notice that it just cancel with one of the h at the top cancels with the h at the bottom, and you're left with something fairly nice. So this is basically the gradient function. This is my f dash of x, or sometimes referred to as dy by dx. And so that's just the reasoning behind why we get this here as the gradient. I'll just quickly go through an example. So we use this example at the start, y equals 3x squared, dy by dx was 6x. But I'll use this same idea here to show why that does just give me that. So hopefully you can see why the gradient is just going to be this thing here. Because as this h gets smaller and smaller, we're getting a better and better approximation to the tangent. And we do just end up with this expression here. So let's just go back. Let's call f of x my 3x squared. Now, we're saying that when at the point x, the y value is 3x squared, we need to get an expression for f of x plus h. And of course, when we want to use the x coordinate as something slightly different, if you remember from GCSE, all we do is substitute this expression into the variable there. So it'd be 3 lots of x plus h all squared. Alright, so that's f of x plus h. So we've got that bit. We've also got f of x, so we can just substitute this now into my expression here. Let's do that. So we know then that f dash of x, so the gradient function basically, it's going to be this, take away this, minus 3x squared. You might be tempted to factorize the 3, but we'll deal with that in a bit, divided by h, and don't forget this limit, because we want that h to get smaller and smaller, because that's how we get the best possible approximation. Okay, right. I'm going to expand this guy now, so I get limit as h tends towards 0. Expand this, I get 3x squared plus 6xh plus 3h squared minus 3x squared. I divide that by the h still sitting at the bottom. Now I'm going to see what I can cancel. Now I can cancel this and this nicely. And now you notice, and if you remember what I said earlier, I said that if you do it properly, you'll notice that the h's cancel off. So there is obviously a factor of h at the top, there's a h at the bottom, and they're going to cancel. So I'm left with now, I'll factorize h so you can see it clearly. I get 6x plus 3h divided by the h. Now I'm going to cancel off the h's there. And cancel them off. I'm left with 6x plus limit as h tends towards 0, 3h, and of course that just goes to 0, and I'm left with 6x, which is exactly what we got up there. And that's it.